Thank you everyone for coming to this ilifu training session. My name is Jeremy and I'm going to be taking you through the first half of it, and then Jordan will introduce himself and take you through the second half. You might know us from the support channels. So just a summary of the topics that we're going to be covering is the user documentation, as well as the ilifu structures and the services. And then we're going to talk about how to access the system and the directory structure, how to find your project folders and how the directory structure is organized. We're going to talk about software containers and how to use software on ilifu. And then we're going to take you through an example of using the Jupyter notebooks, talk about transfers to ilifu. So Jordan's going to cover that, talk about parallelization of code using the SLURM cluster, examples of using the SLURM cluster worker nodes to run jobs. And then at the end, take you through a demonstration of the pipeline and Carter software. So the majority of the work is supposed to be generalized, not just focused on astronomy, but we've left the two specific astronomical topics towards the end of the demo. So just to start off, other thing that we would like to do is, because we have a lot to cover, we're going to leave questions for the end of the session. We'll stay for 15-20 minutes and take questions. So we prefer not to stop to answer questions during the training session, if that's okay. We would like to just start off with showing the documentation. So let me just share the desktop. I will, yeah. Okay. Sorry, so just to indicate to you the support documentation, it's available at docs.ilifu.ac.za. This user documentation is updated regularly, and so it is a very good first point of call if you have any queries or trying to find information. So we do have a request for access, which is where you will find the web form for accessing the system. And then this section, getting started, basically takes you through the steps for using the system for the first time. The structure of this training session is very much based on the structure of this getting started section. And then there's also more advanced topics, topics specific for astronomy, which is the software, Carter and the pipelines, and also transferring data from Soreo to ilifu. Then there's a section specifically for bioinformatics. And then more advanced topics about using singularity containers and software and running jobs in that cluster that you can find below the getting started section. Just to also point out about getting help, please do contact us at support@ilifu.ac.za. This is a fresh desk ticketing system. So if you email this, we receive a ticket and we can help you. We have a large support team that will see to your support issues. Or if you have any questions or queries, you're welcome to email us there. All right. So that was the user documentation that I just went through. Just again, to reiterate, it is regularly updated, so it's good to frequently check what's new. In the future, we intend to send out update emails to let people know of any changes of the way something is done in the system. If that's the case, we'll email all users. So just in terms of the background about the ilifu Research Cloud, it is specifically, well, it has a number of tasks, but one of those tasks is obviously data management. So data is transferred to the cloud environment. A lot of the data that you're obviously working with as astronomers is too large for use in your personal computer. So that's the service that we provide, is storage and transfer of data. And then we also want to provide you with a flexible computer environment so that you can reduce your data or work with your data in a way that meets your requirements. So we aim to be as flexible as possible. And then we obviously support a large variety of scientific projects, both astronomical and bioinformatic projects. And then there are other fields or departments that we also support on request. So just in terms of the structure, we thought it would be important for users to understand the structure of the system that you're using. So in order to service the data transfer, storage, and the flexible compute environments, we obviously have resources, CPUs, RAM and memories, networking levels, storage devices, and these are all controlled by OpenStack, which provides the flexible cloud environment. So on OpenStack, we have systems such as the SLURM cluster, which is a service that provides compute nodes to the users. And then we also have the Jupyter Hub service, which is an IDIA, a development environment where you can code and test scripts prior to launching scripts on the cluster. So those are the two primary services that users interact with. There's also the cluster, for example, is not just for submitting long jobs, but you can also use the SLURM cluster to interactively work in a development environment. You can allocate yourself a compute node for a period where you can do interactive development. So the SLURM cluster is not just for job submission. That's the structure. So just a brief overview of the SLURM structure. So the SLURM Work Manager is what controls and manages jobs on the cluster. So you have a head node, which is what you log into when you SSH into the SLURM cluster. And this is where jobs are submitted from. And then from the SLURM cluster, it's broken down into different partitions and compute nodes. So there's obviously a lot of backend systems, but if I'm just going forward, you can see the breakdown of the head node to which you SSH onto, and then there's different partitions. So the compute nodes are divided into different partitions. At the moment, the partition 1 is the general SLURM partition. Here's the details in terms of what resources are available within there. We have about 60 nodes in the main partition, and each node has 32 CPUs and 236 gigs of RAM. The second partition that's important for users at the moment is the Jupyter spawner partition. You don't actually actively use this partition, but when you're selecting a Jupyter notebook or spawner, that Jupyter node exists inside partition 2. I'll demonstrate that at a later stage. And the Jupyter spawner currently has 10 nodes. So that's the structure. Just to clarify, when you log in to the SLURM head node, you're landing on this head node here. This head node, it's a limited node, doesn't have a lot of resources, so we don't want users to run software on this node, as it'll be detrimental to other users. So what you need to do once you're on the head node, if you want to submit a job, we'll demo that later, but basically jobs and interactive sessions, you need to use the compute nodes that are available, which you can see are in partition 1. So you would request a compute node, and then you can run a job interactively, or through this job submission from the head node, it would allocate a compute node from this partition. So we request that users don't try to run software on the head node, as this can affect the experience of other users. So the other service that we provide, so it's just as a summary, it's the SLURM service, which is a cluster, and the Jupyter service, which is a development interface. We also provide a transfer node. This transfer node is at transfer@idea.ac.za. And so we request that users don't transfer files SCP or rsync from the SLURM head node here. It's best to use the transfer node. I think Jordan will discuss additional information about that at a later stage. So moving ahead, this example of the interaction to work with compute nodes, you would SSH via terminal head node, and this is how you would interact with the compute nodes. And the Jupyter Hub interface provides the IDE. So the ways in which you access the ilifu services is by two processes. It's either through SSH authentication using key pairs. So when you sign up with us, you provide us a SSH key pair, the public key pair. And this is used for the shell terminal, accessing the terminal via shell. And then the other way that you access the system is through your password. So this password is used on Jupyter Lab, the Jupyter interface, and also for the Carter service that's available or that we host on ilifu. If you happen to format your personal computer or you receive a new laptop, you probably will likely lose your SSH key unless you've saved it somewhere. In that case, when you try and SSH into the SLURM cluster, you're going to get a public key denied error, which means you don't have authentication anymore. If that is the case, you need to recreate your SSH key. Let me just show you in the documents where to do that. So here's just information about the SSH key. You can follow these instructions here, and then you can send us your public key again, and we'll update it into the system. Then again, these are examples of accessing the system. So here is an example of SSHing into the SLURM head node. You would, from your terminal, from your laptop, it's SSH and your username at slurm.ilifu.ac.za. And then to access the Jupyter Lab interface, you would go to this URL, jupyter.ilifu.ac.za. Often, if you can't access it, you do need to put the HTTPS in front of it, so it doesn't work without the secure SSL access. In terms of the directory structure, so how I'll go through, I'll do a demo of SSHing and show the directory structure after going through the slide presentation. But the common areas or your user home directories are available at /users. And then the other common area is a Scratch space where you'll also have a user directory. So your home directory is /users. This mount is only a 20 terabyte mount and shared amongst all users. So this home directories are only for small scripts and small files. Please don't transfer data or install large software in the /users section. The Scratch section is for a processing space for you to run data reduction as a user. So you'll have a private user folder in Scratch users in your username. So this is a preferred space for processing. As it is a Scratch space, it's only a temporary storage for data or your products while you're doing processing. Once you have finished processing, we request that people, users, please remove data from Scratch. The Scratch mount, again, is only 100 terabytes at the moment. It should be expanded soon to 300 terabytes. But currently, we request that users remove the data because other users are going to need to place data in the Scratch mount in order to do their processing. The rest of the data structure is group specific. So IDIA is obviously related to the astronomical users. CBio is computational biology, and SANBI is also bioinformatics. So the directory structure is divided up for the IDIA users. For example, there's a larger user space at /IDIA users where you can store data products that are specific to your user. There's also project spaces under IDIA/projects. So you'll get the Thundercat project, the Mighty project, and other projects available there. This is where you'll find access to raw data that has been received from Soraya or data provided to the projects in other ways. Also, this is a space for projects to share their pipeline information or scripts or anything that needs to be shared amongst project users. We have an IDIA software directory, which is where the pipelines is available from, and also the pipeline software, and also the containers that I'll talk about just now is available from IDIA software. And then public data is also available from IDIA Data Public. I think I would like to just do a demo of the structure and an example of SSHing. So from the terminal on your personal computer, you would use SSH your Jeremy at slurm.ilifu.ac.za. This will place you on the head node. So we use Ubuntu as an operating system. So you'll be able to use Linux commands such as ls to list files in your current directory. You can see your path using the current path directory. Also, if you wanted to, for example, make directories, you can do like so, and you can see that I've created this directory here, and I can cd into responsive, not at the moment. Oh, there we go. And you can see, so it's basic Linux commands are available on the SLURM cluster. So you can see when I landed in user Jeremy. So this is your home folder. But again, just to reiterate, please don't put copy large files or data into your home directory. The other obviously data structures that may be relevant is the IDIA for astronomy users. So here you have raw data will be stored in here. Your project would be available from IDIA projects. So there are a number of projects that we have available or that we currently support. And then the space for processing is under scratch/users. And well, let me go into my home direct, well, my Scratch users. So here you will be able to reduce or manage your data processing from the Scratch space. And one last is useful is the IDIA software containers. And so I'm going to speak about this now, but this is where the containers exist. These are software stacks. So let me go ahead. Yeah. So the shell that is default from all users is the bash shell. So just for additional information about the storage infrastructure, currently /users and Scratch is sitting there. Well, we host two types of storage, which is BGFS and CephFS. So currently the mounts users and Scratch are sitting on a BGFS storage system, and then /IDIA and the other groups are sitting on Ceph. So ideally, or BGF is we have less of it, but it's fast and ideal for processing, which is why Scratch is sitting on BGFS. And through kind of early benchmarking tests, we found that processing on BGFS saw about a 15 to 20% speed increase over CephFS. But CephFS is ideal for, we have a lot of Ceph. It has high read speeds and it is ideal for storage. And it's still being optimized in the future. We might see that this processing speeds on Ceph are as equal to BGFS. But at the moment, we recommend undertaking your processing in the Scratch space on the BGFS system. Moving on to the containers. So this is how we support software on SLURM and on Jupyter. We use Singularity containers. These are encapsulated environments where they contain all the software environmental variables, libraries, and dependencies required to run certain applications or workflows. You can imagine them as a container that's filled with different software. What's great about Singularity containers is that they're available across all the platforms. So, for example, if you had to install software yourself on one VM or cluster, sorry, on one virtual machine, and that machine is brought down and brought up again, you're going to lose the software. Whereas Singularity containers are in a shared space, and they provide the software even across the different platforms and between users. So it's great for sharing services and for collaborative work. So that's why we've gone with Singularity containers. It is also possible to use Python virtual environments. So we do have Python installed on all the virtual machines. So if you do want to test Python software, you can create a virtual environment. I haven't documented or going to provide more information about this at the moment, but we may add a more advanced training to cover that at a later stage. So these are the current available containers that we actively support. So Casa is obviously the Casa NRA software. We also provide containers that the Kern suite, which is a large suite of astronomical software. We have containers that are specific to Python 2.7 and Python 3.6, as well as R. So those have general libraries available to those languages. We also provide containers specific for project groups. So these are projects who have approached us to help them develop containers such as the Mielech, Laduma, and the H1 intensity map. So we do welcome users as project members to approach us if they need assistance with container development. Then these containers are available in the system, and all the users who are part of a project have access to them. So just to go to the documentation, I just want to show information that about the directory structure, to show where to find this documentation that's also detailed here, and then information about the software containers and how to access the software containers. So all this information that I'm going through is available in the documentation. So let me go back 2 slides. So for using a container, it's a simple command. So here, there's a number of ways to use a command, a container. So there's the shell command, which places you inside an interactive shell session inside the container. So here, running from the terminal line, you would go Singularity shell and then the path to the container. So here I'm using source finding container. You can also directly call a container to run a Python script. So here, for example, I'm executing the container. I'm calling the Casa stable container, and I'm requesting that the Casa software run my script.py. So this is 2 different ways in order to use the container software on the system. So this second one is how you would submit jobs, but Jordan will on the cluster, but Jordan will discuss that at a later stage. And then just to make note that Singularity is not available on the SLURM login node. So in keeping with our need to not run software on the head node, Singularity is not available. So you do need to access a compute node in order to run a Singularity container. So let me just demonstrate that. A very simple way to get a compute node is to run srun.pty bash. This requests a compute node with the default resources and requires like a pseudo terminal in bash. So now you can see that I've been placed on a SLURM worker. You can see the prefix has changed. So if let me just go back to my home directory, and if I go Singularity shell IDIA software containers and say I want to use the Kern 5. So this will put me into the Kern container. while that's going on, oh, there you go. It's just finished. So here you can see that I'm sitting inside the current container. This will have Casa Lite, I believe, is available from, and other software. You can see that's available in the container that isn't available in the cluster without the container. So none of the software, for example, is installed outside of the container. So you can open Casa now, and you can interact with Casa. You can open data from inside the container. So in the container, you obviously have access to your directory and all the IDIA project directory. So all of this is available inside the container. So you can interactively run Casa and list obs on astronomical data as you need. So that's just a quick example of how to use the Singularity containers. There's also, let me just show an example of the Python 3. So if you want to find information about what software is available in the container, there are 2 ways. So on the documentation, we have software containers. The bottom here, supported software environments. So this is just information, additional information about how to use containers, the interactive shell command, the exec command, and how to run Singularity on the cluster. Just over here, point out available containers. You can find information about what's inside the containers by using this arrow drop-down menu. So it lists the, this is specifically an R container, but the others, for example, will list the Python packages that are available in the container, as well as the software that's installed in the container. So that's very useful. But alternatively, if you go into a container and you do a pip freeze less, it'll also indicate to you what Python packages have been installed. So if you're looking for software, you can investigate the containers or search in the documentation to find if a package or library is available. The Singularity containers are relatively simple. So here are the different, obviously the Python packages that are available. You can build your own container. There's information on the user documentation. So it's a script very similar to a Docker script. So there's just different sections. So the main, or what's probably most clear, is that this is the list of commands that you would install or you would run in order to build the environment. So similar to if you had a fresh install of Ubuntu and you wanted to install different software, this is how you would include it in the container. You could make directories, you can build software by following the installation instructions for specific software. So it's each one of these commands is executed during the build of the container, and then this software will be available once the container is built. The other sections are ways to copy files from the outside root operating system into the container. And the environment section is where you would set environmental variables that you want available in the paths once the container is built. So you are able to build your own containers and then make them available on the SLURM cluster. Alternatively, please do approach us for assistance with that. And then I'm going to move on and demonstrate the Jupyter environment. Yeah, cool. Just consulting my notes that I've covered everything. Cool. So, before I go on, just in terms of the cluster. So if I'm sitting from a worker node, I could use this from a worker node or from the head node. Just some basic commands, for example, sinfo will provide me info about the cluster. So this is the main partition that I spoke about early on, and has about 60 different compute nodes inside of it. You can see that these are the idle ones currently, but these are currently have jobs, either they're fully allocated or they are some spaces available in these compute nodes, so they're indicated as mixed. And here, for example, is the 10 nodes that are specific to the Jupyter spawner. So when I'm going to demo it now, but when you create a Jupyter spawner, they use these resources. And then, so I will demo if I have, the other useful, well, S obviously stands for SLURM. So here lists the SLURM queue. So here is all the jobs currently running on the SLURM queue. You can use sq-u Jeremy, your username, and you can see what you're currently using. Currently, I'm not running any jobs, but I'll show you once I spawn a Jupyter notebook that the job will appear here. So just to demo that. I believe I've logged out. Or let me start a new one. So when you want to use Jupyter, this is the URL that you'll use, and then you are taken to the login page. So you'll use your ilifu credentials, your username and the password that you've been provided. You can obviously change your password. You just need to do it from the terminal using the password command. There's information about that, and it's highly recommended to please change your password. So from the terminal, just use that command to change your password. So once you've logged in, you'll be placed on the options page for the spawner. Here you can select different size nodes to spawn. The max node is 32, so this uses a full node, and then they're divided by kind of halves of those values. And the nodes they run for 72 hours, so for 3 days. I'm just going to demo with a minimum node. So here you can just select the node and then click spawn. We do request users to only use the resources that they require, as opposed to always going for a max node. However, I have found working with large data that a minimum node of 4 gigabytes memory often throws memory errors. So if you do experience that kind of thing, do scale up to a large node, but do try to make use of the smallest number of resources possible, as there are a large number of users. We click spawn, and this will take you to the launch space. Information in the user documentation is available here for using Jupyter Lab. You will notice that when we get in to the hub, that you'll see a number of kernels that you can choose to start your notebook. These kernels are actually using the Python that's available in the Singularity containers. For example, AstroPy uses the source binding container. AstroR will use the AstroR container that we have. You can also spin up the kernel containers as Jupyter Notebook. So the software, the Python that's available in these containers is what's being used in your Jupyter Notebook. And in addition, you can actually access the software that's available in the container from the Jupyter Notebook. So this is the launch space. You'll see the kernels here and with their names. I also have a number of custom kernels, and you're able to create custom kernels for yourself too. This is listed in the documentation. But for example, to start up a Jupyter Notebook, I would choose a specific kernel, and it opens a new notebook. And here, for example, I could import AstroPy or run and do development using the Python or the Python packages and the libraries that are available in this kernel. So similar to the terminal, you can also, if you use a exclamation mark before a command, it will send this command to the operating system. So similar to viewing the packages from the terminal, you can also run a pip freeze, and it'll list what packages are currently available in this container. So that's a useful trick to finding what's available in the container. You can also do things like pwd to see your current directory path. And so what I'm doing here is if you haven't used Jupyter before, what's nice about Jupyter is that you're able to do sections of code. So you can type and then run the command. So the shortcut is Shift Enter, but you can also use run selected cell here. And you can do development in a very step-by-step method. So this is one of the benefits of Jupyter. There's also, if I view the launcher, there's also a terminal available in Jupyter. So here you can see terminal command. So this is in the web browser. And you can see that I'm sitting on a SLURM worker here. So if I go to the SLURM head node and I do SQ for you, Jeremy, here, I can now see that I'm actually running a job and it's being placed on SLURM worker. So my Jupyter session is running on a compute node on the SLURM cluster. And you can do, this is bash shell, so you can do similar commands from this terminal. And it's an easy way to copy or move directories or data just using the Jupyter hub space. So just as an example, here is an example notebook, very simple, importing libraries, writing some code, plotting sine wave. You can look at variables in the Jupyter IDE, etc. And I'm not going to demo how to create your custom kernels. The information is inside in the more advanced topics for software environments. So it is under the section using a custom container as the Jupyter kernel. So this uses a container, but you also can use custom virtual environments that you have built with Python. And you can also do a similar setup and create a kernel in Jupyter using the virtual environments that you have created on the cluster. Also note that Jupyter is not just Python. Obviously, you can install other languages such as Julia, Go, Ruby, Erlang. There's a number of different languages that Jupyter supports. And then it is highly recommended, especially if you're using a max node, to please end your Jupyter session. So because when you spawn a Jupyter session, they last for 72 days. I'm sorry, 72 days, 72 hours. If you stop using, or if it's sitting idle, you're still utilizing the resources. So we please request that users end their sessions when the Jupyter sessions are not in use. So to do that, you go to Hub Control Panel. And this will take you to a page where you can stop your server. And this will free up resources for other users.
While that loads, it could be cool to share if you like to have completion and putting up the docs. Any experience with it?
What do you mean tab condition?
In like SL in Jupyter?
Oh, like
No, in Jupyter.
in Jupyter.
Yeah, I think that will be a few later.
Do you mean tab conditions for like imports and stuff? Or
yeah, and the functions and stuff.
Oh, right. Oh, you mean like looking at different package information and stuff?
So if you just do like dot tab,
yeah.
for instance,
Dot.
BLT.
Thank you.
Have you run any of these?
No, I haven't. You're right.
Running these plots. So,
so the IDE will show you the different functions that are available to the package. And you can also do a question at the end, and it'll automatically give you the docs for that particular function, which is a really useful thing to have in an IDE. So it is, yeah, it's very useful. There you go. So stop my server to end your spawn session. If I go here and I check if I have one, no, hasn't gone through yet. But okay, just as an example, this is how you would stop your server, and it would free up the resources that your Jupyter session is currently using. And then if you start your server again, the tabs that you had available before will be open. So it does save output, and it does save the tabs that you were working on. It captures that information as a config in your user folder. And so when you start a new spawner, that's terrible. When you start a new spawner, what you were working on and your output will be visible inside the notebook. But I am going to let Jordan take over. Jordan's going to talk to you about transferring data to and from the ilifu cluster, as well as using SLURM, submitting jobs on the cluster, and also about the astronomical IDIA pipeline software and Carter. So that's me. And then we'll have a question session at the end if anyone has any questions. So I'm going to stop sharing and hand over to Jordan.
Cool. Do you want to mute and mute?
I am muting.
Cool. Everyone hear me okay? Someone just mind posting in the chat if they can hear me. Yep, cool, thanks. All right, so I'm gonna plug in first. Everyone can see me. Yeah, for this second half, I'm mainly gonna do some demo type stuff. As Jeremy said, we'll go through transferring data, parallelism and SLURM, and then I'll demonstrate the IDIA Meerkat pipeline, not so much as an astronomical software, but more to do with the framework, the way in which it's used to submit jobs to SLURM, and yeah, is able to take different containers and run steps that do or don't use MPI.
You could maybe show this up to the screen here.
Yeah, it'd definitely be better like this. We tested it just before. I'm not sure. Yeah, there we go. Cool, good. All right, so that's pretty much what we want. Okay.
You can show your screen.
Oh yeah, sorry. I haven't shared my screen yet. Sorry, guys. Share desktop too. Cool. So just picking up from where Jeremy left off, so this is the kind of biased data flow that I'm going to present, biased because it's astronomy and Meerkat. But I guess generally I want to talk about transferring data, processing data, visualizing data, all of which is done within ilifu rather than on your own machines and laptops. This is a fairly generic data flow. So firstly, just to point you to the docs for the data transfer. So this is on the same documentation website Jeremy presented. So it goes through using SCP and rsync as well as using Globus. I'm going to be covering both of these. So the first idea I want to mention is to please not use the head node. Jeremy already mentioned this, but we really do stress this, that you will congest the head node for everyone if you SCP there. And so that's why we've set up this transfer.ilifu.ac.za node. And this is for you to run SCP and rsync. So for instance, the syntax that I've listed here, you find some file that you're wanting to transfer, and then you transfer to some directory, for instance, some scripts directory that you might have on ilifu. And the idea is that you will transfer such files as scripts and config files and not larger files. And in particular, don't write those larger files to /users. Even if you're using Globus, which is for larger files, please don't write that to /users. And so, as the docs say, the SCP and rsync is generally for files maybe up to 200 gig or for less frequent transferring. But if you're doing any kind of frequent transferring, I do suggest that you get set up with Globus. So Globus is faster than SCP and rsync. It uses a grid FTP backend. And so this means that it's a very efficient transfer, but it's also very user-friendly. This is actually the same protocol that we use to transfer Meerkat observations from Soreo to IDIA to ilifu. And currently we're actually extending this to collaborators in the UK, Netherlands, Italy, and India. But we're also making available to all users a Globus online service. So this is where you can go and register for a free Globus online account, and you can connect the ilifu DTN as an endpoint, and you can do all this in a very user-friendly way, which I'll demonstrate in a moment on the web app. There's also a command line interface, but for most users they'll probably want to use the web app. And it has a server version, which you can use if you're connecting to another server or data transfer node. But then if you're just using your desktop, you can download an app for Mac OS X, Windows, and Linux. So just to demonstrate that briefly now. So I have, you can see it very nicely, but I've installed Globus on my laptop. So this is done by following the instructions in the docs. It's very easy. You can log in with your university credentials, or you can register a specific Globus account. You then type in ilifu, you find the DTN, you log in with your same credentials as you would to Jupyter Hub, and then you find your files. You're able to find them through the web app. And then you set up another endpoint on your desktop, which is following, for instance, if you're on Mac, we've linked to the Globus documentation here. Literally punch in a name for your endpoint, generate a key, copy that key, download the Mac OS X version of the download, you then drag it into applications, open the thing, paste in your key, configure it to which files you want to be visible. For instance, I just do my downloads folder, and then that's all in the preferences, and then you're ready to go, basically. So it's very user-friendly. And so just to briefly demonstrate that, so I'm going to go web transfer files. And this pulls up the Globus web interface. And so for instance, I suppose if I click on the ilifu DTN, so this will pull up my directory structure. You can see I can view everything in my home directory. I can also go /scratch users J Collier. I can also, there's one that I've bookmarked over here, so I can go to ilifu demo, which is okay, that's a good start. I think I actually changed the path, sorry about that. Got to update this. So I believe it should be demos /globus demo. Need to update that bookmark. Okay, maybe not. Let's just navigate to it through the GUI. Okay, so this is interesting. So I should be able to go back to my endpoint and just refresh this. You have to do this once in a while. So I go to ilifu DTN. And then it pulls this up and okay, no, so it says I'm activated for another 5 hours. I'm not quite sure what was happening there. You can just navigate through this way. So I would take a file, so for instance in this directory, this is a symbolic link to a Scratch directory that I have. And so I might navigate to one of those, and then I might find a file that I'd like to transfer. So there should be an images directory here. So I'll go to that. And I'll find an image that I'd like to transfer. It's really small here on this screen's resolution. I'm not quite sure what this file is because it's cut it off, but nonetheless, let's choose that. And then I'll say transfer or sync to, and then I'll find a collection. I'll choose my laptop, which I've configured. And then, for instance, I'll go to Globus demo. And then I'm saying, okay, let's start the transfer from this side to this side. And then I get this link, I can click on that and it'll show me, for instance, in the event log, I start to see the wheel spinning up here. So you can see whether anything went wrong. See the transfer started now, view the details. And then at the end of this, I also get an email to say that it's either successfully transferred or that it's failed. And then I can also do, so, okay, this is permission denied, that's not good. Path not allowed. Okay, I'm not really sure what's going on here, but I guess for the purposes of this demonstration, this doesn't happen generally, so let's just leave it at that. I have to pull up my bookmarks, here we go. And then I can do the same from, for instance, collection on this side is my laptop. And then, you know, inside this, I already had a file. I could say, okay, start the transfer from, change my endpoint to ilifu DTN, and then choose some, and then I follow the same process. So you're able to do it both ways. I could start this transfer, go from there to there, monitor the status of that, and then again get an email saying whether that's worked or not. So the idea is that it's quite user-friendly for just browsing through your files using the file browser. And even though it's user-friendly, it's using quite a powerful back-end grid FTP transfer protocol to do so efficiently. Yep, so that's Globus. Moving on to parallelism. So I found the Oxford definition for parallel processing quite useful. It's a mode of operation in which a process is split into parts which are executed simultaneously on different processes attached to the same computer. So this is really the idea of parallel processing. It's where the work to be done within a process is partitioned into smaller jobs, each managed in our setup on a different SLURM worker node or a different CPU or task within one of those nodes. And sometimes each of those receive a partition of the data set itself, depending on how the partitioning is done. And so this could be either parallel processing on a single machine or a single node distributed over many CPUs. And this is typically implemented with OpenMP. This is an open source software for managing multi-CPU processing. And so, as I'll demonstrate in a moment, we can do that using SLURM on ilifu on a single node. Or you can also distribute processes over many machines or nodes on a cluster. So this will take many different tasks, and you will use at least one node, but maybe multiple nodes. Each of those workers is given a different amount of memory to use, either as partitioned from a total memory you've given it, or perhaps you've given it a memory per CPU, or amount of memory per task. So generally this requires a cluster, and generally it's implemented using OpenMPI, and this is again an open source message passing interface software. So message passing interface, or MPI, is what manages the communication of the jobs across multiple nodes, because they need to communicate with each other and know where they're up to and how they're going. Often this will also require a master worker that manages all the various workers that have gone out and done their processing. So this means that we need an MPI wrapper to run such a job. So for instance, we have MPI run or AP run. SLURM uses srun, and if you're using the radio astronomy package CASA, then you would use MPI CASA. So for ilifu, this is all managed by SLURM. So for a normal job, which for many processes is the default, we'll only be using one CPU, one task, and one node. Unless you know that something like OpenMP is implemented for your program, then you would generally do this. Or if you know that MPI is implemented, you would do this first case. If you do have, for instance, an OpenMP implementation of your program, you would use more than one CPU, while you would use one task and one node. Unless you're also doing MPI and OpenMP type processing, these would be one, while the CPUs would be more than one. So this is the CPUs per task, parameter in whatever you're running, srun, for instance, or sbatch, as I'll go to demonstrate. You might also need to export OMP num threads, so OpenMP num threads. So this tells OpenMP how many threads that it's using. I think this is just a generally good habit to get into. So you would do export OMP num threads equals 8 or something like that inside your script or sbatch job or whatever it is, or inside just your shell, your terminal. If you're implementing an MPI job in SLURM, then you're using more than one task per node, which is the n task per node parameter, but you would maybe be using one CPU and one node, or maybe many nodes. Generally, you're either doing many CPUs or many tasks. Some software does both. So that takes us to SLURM. Let's drag this over. So these are the docs pages on SLURM. It's quite extensive, shows you how to use, how to write an SBatch file, what the different parameters mean, how to launch them, how to view progress, how to launch an interactive session with and without X11, for instance, X forwarding some visualization in some way. So I just want to flash those up so that you know that you can refer to those. Yeah, so as Jeremy mentioned, the head node is what manages the job submission and the jobs themselves, which will go to one of the partitions, either the SLURM partition, which is actually a few partitions, or you're using Jupyter, and in the background, this is all being managed by SLURM. And as yeah, Jeremy said, one is Jupyter Hub and the other is SSH. So there are many user commands, which I think go to this URL to view those and the syntax and what they do. So Jeremy's already demonstrated SQ, sinfo. I'll demonstrate SBatch in a moment. We can also cancel a job with scancel after it's been launched. And then this scontrol show job ID is quite useful to show information about that job, like what you've requested for that job in terms of resources, as well as some information about its status. And so the best way generally to write a SLURM job is to write an SBatch file like this, which I'll demonstrate in a moment. So generally we have these parameters here as a minimum, which describe the job and the resources being requested. So I give it a name. So in the queue it will be given this name. I give it the number of tasks, which again is more than one if I'm able to use MPI. And I give it a number of CPUs per task, which is greater than one if I'm using something like OpenMP. And then I give it, for instance, a memory per CPU, or maybe a total memory for the job. I write this output file. So this is where standard out is going to go to. What would normally print on your terminal goes to a file, and you can read it there. You can view it in real time while the job's running. And then I write my standard error, which again is usually printed to terminal when an error happens. I write that to a separate file. So that's what these parameters are describing. And then I might, for instance, call singularity. And so I specify my container, I specify the software I'm using, and then the script that I'm passing in. And so this is what's being run, and this is what's being allocated as resources. So the way I would launch that is with this syntax, SBatch, and then the name of the file. But then I might also, for instance, use, as I say, this radio astronomy software CASA. So I would specify a different container, and for this it takes a script as a configuration for running CASA. We can also run interactive jobs, which I showed you where that is in the docs. There's a few ways to do this. Jeremy demonstrated srun pty bash, which is essentially exactly the same as what happens when you run salloc. And so this is a way to allocate yourself resources. The default is 1 task, 1 CPU, and 8 gigs of RAM. But you can also specify different configurations for those parameters. And then you can also even call a singularity container. For instance, this CASA software we could launch like this. And so this would give me an interactive CASA session. You can view the parameters that you can input with help, or you can go to the SLURM docs. If I want X11 support, which would be some kind of X forwarding of some visualization, then I may have to first run this SSH add option K. This is for if you've actually copied a key from an old machine to a new one, you have to do this. So generally, like Jeremy said, if you do get a new machine, it's just easiest to generate a new key and send that to us. But if you've copied it like I did, then you have to run this, capital K for Mac OS X, lowercase k for Linux. And then you SSH with options Y and A. So this is important for X forwarding and agent forwarding. And then you would call SLURM again, but you'd pass in these arguments, which are telling you to allow for exporting from the worker node itself. And again, those have the defaults we mentioned, or you can pass in your own parameters. So some general advice if you are running SLURM jobs. Firstly, identify the resources that are available. You can do that with sinfo. So you could see, for instance, whether much of the cluster is being used, and you may want your job to run instantly, but you can afford to have fewer resources, and so you would minimize that. We also don't want users to hog the cluster. So if you can, we would like you to reduce your resource allocation to be something that's not basically the whole cluster. And then, yeah, obviously, as I say, use SLURM or SRun PGY for interactive jobs. Don't just SSH onto the worker node to have an interactive job. You might think this is better than doing it on the head node, but it's not actually necessarily, because this would take away from resources that other people have already allocated themselves in SLURM by SSHing onto the node and running a process without using SLURM or SRun. Then you're actually taking away those resources that have already been allocated or may have been allocated to someone else. And we do monitor this, and if you are doing such a thing, we will kill your job. All right, so time for some demos. I'm just going to drag this over. Can you see that? Yep. No, I mean I can zoom. I can maximize it there if that's useful. Yep. Cool, so I'm just going to connect to the ilifu cluster. I'm just kind of thinking here. Oh, there we go. The bottom's cut up, okay. I'll just bring that up a little. Is that good? Yeah. All right. So, yeah, so I'm just going to go to my Scratch directory. Good start. Cool, and this is that demos directory that Globus wasn't happy about finding. So first I'm going to do this SLURM demo. So for SRun, one of the things I often do is I write an HDF5 file that what I'll show later, Carter can view. So this is just this tiny little script that I wrote. So I'm just going to demonstrate this. So here I'm running SRun. I'm requesting 1 GB of memory in total, only one node and one task per node, and a maximum of 10 minutes. If it goes over this, the job gets killed by SLURM. And then I'm asking for 32 CPUs per task, because this software actually uses OpenMP. And so then I'm going to grab an image file. Oops, images. Okay. Oops. I'm not sure why that's happening. Oh yeah, I've got it, that's right. So this is an image that came from Quick Look Imaging from a pipeline that I'll show later. So I specify the name of the FITS file, and then I'm just going to say im.hdf5. And so I run that with SRun, and then it's allocated me those resources on a compute node, and it's run the process extremely quickly. And so now I've got this im.hdf5 file. So that's how we run SRun, and you can configure those parameters in different ways. As I say, only one for a lot of processes that don't use OpenMP, or for something that implements MPI, we'd use more than one task and then perhaps more than one node. Generally, if you're doing that, though, you should write an SBatch file. Here's an example SBatch file that I stole from Jeremy, and this is the one that I showed before. So here we've requested these resources, and we've specified this kind of output file and name of the job. So this calls this container and executes this script. You can see this script is just import time, print hello from the container, and then sleep for 30 seconds. So I'm going to run, oops, snatch. I'm going to run that with SBatch SLURM job script. So that's launch that. This is my job ID. So I can, for instance, run SQ for my username, and you can see it's showing that running on SLURM Worker 101. I can also, for instance, if I don't want to see all of my jobs, I can specify this. Oh, sorry, I copied that. I can specify, just show me that job rather than all the jobs that I have running. So you'll see, okay, I'm not sure what's going on there. Okay. Implied that it had before. Yep, so this will launch hopefully in a moment. While we're at it, let's check what's available. Yep, so there's still 24 idle nodes on the main partition. And this should... Okay, I'm not going to waste your time waiting for this to run. I'll demonstrate some other stuff and then we can come back to that. Let me just make sure it hasn't started launching, no. So another thing I can do is salloc. So yeah, I showed you that before. So we just type salloc and then we run. And so this requests resources with the default parameters. And this would put me on a compute node, so I'm able to run processes interactively there. Now this will not by default allow for exporting because that's the other syntax that we mentioned before is needed. I'm just going to Control-C this and go on to the test partition, see if that gives me any more luck. Cool. So I've been granted the resources and then it puts me on SLURM Worker 159. So now I can run a process here. I'm not going to do that, but if you have a look, I now have in the queue, I've got on the test partition this bash session that I'm running here. And so this is actually reserved the resources. And so now no one else can claim those resources unless they SSH and then we'll kill them.
Yeah.
Okay, yeah, thanks. So I'll just exit that. You can see this is running now. So you can see, for instance, there's nothing in standard error. I look at the standard out. You can see submitting demo SLURM job hello from the container because in our SBatch job, we just echoed submitting the job, and then in my script, we just printed hello from the container. So you can see that was in the queue, and now I can run saccount. So this by default will show the jobs that I've run. This is showing some tests I was doing yesterday as well. And again, if we want to look at a specific job, so this demo job, we can saccount option J, that job, and it'll show me this. Now what I do want to show, I'll just scroll up here. When we run SQ, you can see the nodes that you've requested in case you forget or in case you want to look at what other people are doing. You can see the nodes that are being requested. And here you can see the CPUs that are being requested in saccount. So saccount is jobs you've run. It gives you a slightly different view of those. It's also ones that have completed, while SQ is only those that are still in the queue being run. So saccount shows you CPUs by default. SQ shows you nodes by default. Now you can, for instance, I have this summary alias. You can output all sorts of information. So for instance, what I like to do is look at some statistics to do with that job, like the max disk read and write, memory usage, number of CPUs, tasks, and node. This was all 1 for the stuff I was doing in the demo job. So it's quite useful to see those statistics. And then, yeah, just lastly, again, I believe I have another alias for this, sviz. So this is the way that you would use, allocate yourself an interactive session on a worker node, but also allow for X forwarding. And so this is the syntax for that, as you will find in the docs. And so this is hopefully opening Xterm for me, which we'll see. Oh no, I guess I have to launch the program first. So it's put me on the node. I can, for instance, start CASA, and then once this is launched, which unfortunately takes a moment to launch, I would be able to start something that has X forwarding, like plot-ms. So I'll just demonstrate that in a moment. Should have just done XIs. So we could run plot-ms, for instance, and then this will start to open Xterm. There we go. And then this would open this window here. So this is now using the resources of the worker node that I've allocated myself, but it's giving me this interactive X forwarding session. So that's quite a useful thing for a lot of different things that you might want to visualize. Cool, so that's that. Next I want to just briefly, I think I have a slide for this, briefly mention the pipeline. So again, this is not so much something I want to demonstrate specifically for astronomy users, but rather the framework. So our pipeline, you can read all about it at this link. You can look at the docs, but essentially it's a parallelized package for high-performance computing processing using SLURM and our cluster. It uses these multi-measurement set formats to parallelize across our cluster. You basically push the button and you get your output calibrated data, and the pipeline itself dynamically allocates resources and submits to the queue. Each job, that is SBatch job, which itself, each of those call a different script, they're all logical steps that do or don't use MPI. And optionally, you can insert your own container for each of those SBatch jobs. You can insert different ones. You can also put your own scripts in any point in the pipeline. So you might have a script you've written that you want to insert into that pipeline, and you can do so. I think the framework is quite cool. So I'm just going to go to pipeline demo. This is just an empty directory. Here's one I prepared earlier. So this is the way that you run it. You can ignore all this verbose output at the beginning, but basically what's being done now is this srun command, which calls this singularity container, which calls this CASA software, which executes this script and then passes in these configuration parameters, these command line parameters to that script. And so this is basically an initialization step of our pipeline to extract certain information from a data set to know how to run it. So we'll see the output of that in a moment, and then we'll be able to see how it kind of builds the pipeline to submit the SLURM jobs. Yep, so there's various output about optimizing the parameters. So this is all sorts of things that we have. Don't worry too much about this. That's pretty astronomy specific. But here are all the SLURM configuration parameters. So it's telling us how many nodes we're requesting, task per node. Plane is to do with the way in which those jobs are distributed. So 2 at a time on a node, and then it'll move to another node. It will put another 2 tasks on, and so on. The total memory in gigabytes, the partition we're using, the time for each job, and then what default container and MPI wrapper we use for, in the ladder for MPI jobs. We can give a name for that in the queue, and then these are those scripts that are run for each SBatch stage. And so I can then run that with run, and you'll see it's written all of these SBatch files. And I'm just going to quickly turn verbose off so we don't get too overwhelmed with the output. I'm going to run that again. So you can see, for instance, this first step, validate input, is very small, just requires 1 CPU per task, 1 node, and 1 task per node. And then I explicitly export 1 OMP num thread, and then I just run this really simple script to make sure the input is right. But then we have things like flag round 1, and this uses many more. So this uses 12 nodes and 4 tasks per node, but only 1 CPU per task, and that's because I have this MPI wrapper. So it's able to do many tasks in parallel. And then, for instance, I have this quick tclean, and this does both. This does many CPUs and many tasks and many nodes. And then in this case, I export 8 LNP num threads. And so this does both levels of parallelism. And so I then go and I've got this submit pipeline script. And what I want to demonstrate here is that you can submit a job with a dependency. So I submit SBatch, and then I just extract the job ID. And then the next job I submit has this after OK IDs, and kill on invalid dep is yes. So this just means that this job has a dependency on the previous job. So once the previous job finishes, if it finishes successfully, then it will launch the next job. But if it finishes unsuccessfully, it will kill and cancel this next job. And so this is a way to launch jobs with dependencies. You can get as complicated as you want with these dependencies, as we're planning to do in future pipeline development. And you can get this whole tree of dependencies, which is usually best to script. And so that's the way that we run our pipeline. Suppose I could quickly demonstrate that gets run. You get this summary script, which is currently not showing anything because it's been quite slow, but you get all these job IDs for the jobs that are being run. I could check if that's, yeah, so it's now running the first, and you see all of these other jobs are in the queue, but not using any resources because they all have dependencies. And so I should be able to run this summary now, and it shows me this one's running, these ones are pending. So that's how you use job dependencies. Just check the notes here. And then just, I guess, quickly to point out, I'm going to kill that because I'm not actually interested in running that job. So I'm going to kill those jobs, and then you can see these will, in a moment, all get cancelled. What I also want to demonstrate is here, when I have false and this empty string. So false means this doesn't use MPI, true means it does. And so this means that it'll insert the correct MPI wrapper, and then the empty string just means that it's going to use the default container. But I could insert any container here and it would use that container. So I think this is a really good way to write a pipeline. And if you're interested in using the same code base that we've used, then you can go to the docs that I flashed up before, and you can use our pipeline code. Cool, that's that. Lastly, I want to finish with Kata. So this is a cube analysis and rendering tool for astronomy. So it's to view images. Supports all these image formats. It's cloud-based, and so it means that the user doesn't need to copy the data to their own machine to try and visualize it, but it's essentially the data, rather than the data being brought to them, they're brought to the data And so we've got docs for using, sorry, this keeps going to the wrong page. So we've got docs for Kata, where to go, what URL to go to run Kata, and then how to convert to one of these HDF5 files that Kata uses. So this is the URL. And so you log in with your same credentials as for Jupyter Hub. And so Chrome's remembered that for me. And I'll bring up the file browser. Now only, just quickly show you this, only Kata share is mounted. So that means that you need to move data to there. In fact, you should just write a HDF5 file to Kata share, either, for instance, in your user directory or perhaps in a group directory. Because the data has to be copied anyway, you may as well copy it to be an efficient file for Kata to read. So for instance, that's what I did in this groups directory. Is one of the output files from an earlier round. This screen is so bad in resolution. I think this is the one. Let's find out. So this was output from self-calibration scripts that we're prototyping for the pipeline. And so you can see I basically run out of time to demonstrate many of these features, but it's all well documented. And maybe if there's a question later about Kata and different ways to use it, we could go through that. But just maybe to demonstrate, it's best to use for cubes. So cubes are where you have many frequency channels. And yeah, for instance, I can go to this public directory and pull up a HDF5 cube, which also happens to have channels in Stokes space. And so you can see here, it's really minimized because of this projector's resolution, but you can step through those channels and it gives you this Z profile, which is in the direction of frequency. There's a lot of other really cool operations that you can do with Kata. If we get time during question time, I could demonstrate some of those later. Anyway, that's everything we wanted to show you. I should just say, even if you're using a continuum single channel image, you should still convert to HDF5. There's still performance improvements there. So I guess we can now take questions both in the room and on Zoom. So you just have to first unmute your microphone if you've got a question, or perhaps you could paste it in the chat. I guess that's formally the end of our time together, but we are allowing for questions now. But if you do need to run off, then please do feel free to do that. So why don't we start on Zoom? Are there any questions? Sorry?
Sometimes you may want to transfer data using the file transfer.
FTP is not supported, but SCP and rsync is supported.
Can you just repeat that question? We can't hear from the side.
Sure. So the question was whether other file transfer software was available, such as, is it Mozilla? FileZilla. So the current services or tools that are available is SCP and rsync. So it depends on the protocol that the file transfer software uses. So I think if FileZilla uses FTP, I don't think you can use it on the transfer node. But if the software uses SCP, you would be able to. I think maybe Putty for users SCP. I'm not 100% sure.
Okay, we got a couple of questions in the chat. So Sebastian's asked, is it possible to spawn different Jupyter Hub instances? For example, if you're working on 2 projects with different data and requirements. So I believe the answer is yes, and it's like, no, not on the spawner. Okay.
No, you can only ever have one Jupyter Hub instance running.
Sure, but I guess that's not stopping you from running.
So you can have different kernels. Yeah,
kernels,
you can have multiple kernels running, which allow. So you can say have the source finding kernel associated with one notebook that you're doing development in, and then you could have like the kern or the Casa kernel active in another notebook. However, when you're spawning a Jupyter session, you can't spawn more than one session. So you're restricted to the resources that you've requested originally. And so if you're running 2 tasks, or 2 notebooks at the same time, they're going to be using the same resources.
Yeah, thanks. So if you're going to do many, it might be worthwhile allocating yourself a larger set of resources, and then you can run many notebooks. There's another question. Yeah, just a reminder, SBatch can be run on the head node, and there's no need for a worker node to run an SBatch job. Yes, that's correct.
Yeah, so from the head node is really for managing and submitting jobs. So you can run SBatch and SRun from the head node and SLR. So what that does is that you're requesting resources, or you're submitting jobs to the SLURM work manager, and it will then assign you a work node or compute node. So yes, you can submit an SBatch from the head node. And you can also run all the SQ and SInfo. I believe you also can submit jobs from a compute node as well.
Great. There was a question, is the recording going to be made available? That is the plan. This will kind of become like an online training that people can refer back to. And we would love to share the presentations that we had as well there, likely on the ilifu website. Although I would stress that the docs are way better than the presentations. You can find everything that you need there. There's maybe 1 or 2 very minor things that aren't in the docs that we did present, but we would like to put them in the docs anyway. So yeah, they would be a better resource. And then another question, is there a tidy way to exit Kata, or do you just close the browser window? I think just closing the browser window is fine. It basically restarts your session every time you go back to it anyway.
The Kata service is not hosted on the SLURM cluster. It's hosted as a separate service. So you're not using resources you're not using resources that could be allocated to other users by using Kata. So you shouldn't have an issue with starting and closing Kata.
Yep, another question here.
So you said several times that we should run jobs from the head node. I don't actually know what that means, so I don't know if I'm wrong.
Okay, so the question, just to repeat, was what does it mean to run jobs on the head node? And so Jacinta's just asking, she doesn't know what that means, so you need to clarify that. So you need to submit jobs from the head node. But what we don't want is people to run software on the head node. So don't open Casa, don't open Python on the head node. Don't SCP from the head node.
Okay, so if I have a file with Jupyter.py,
yeah.
I log into SLURM and I go cp/IDIA/u/Jupyter and I do Python Jupyter.py. Is that running from the head node?
That's running on the head node. What you need to do is you need to either submit that Python script as a job to the SLURM work manager. So that's the SBatch script. Or you need to assign yourself a compute node using SRun, which is like an interactive way to give yourself resources on a compute node, and then you can run your Python script.
But my Python script is not parallel straight up.
Yeah.
Yeah.
So the default resources on SBatch and SRun and SLURM is 1 task, 1 CPU, and 8 gigabytes of memory. So if that is enough for your job, then you don't have to specify your requirements. But if you want to increase the memory, or if you're using, if your Python script uses OpenNP, you can obviously increase the number of CPUs that you would need.
And how would you choose between SRun, SLURM, and SBatch?
So SBatch is when you're submitting a job to the SLURM work manager that you're not expecting interactivity with. So it submits the job, and you still have control of your terminal basically, and you can submit another job, and that job will be pushed to the queue, and you'll either receive the output when it's finished, or you can monitor your job, but the job's running in the background. So for SRun, if you use SRun or SLURM, what you're doing is you're requesting like an interactive terminal on the compute node. So there your terminal will be utilized to run that job, if that makes sense. So if you and the difference between SRun and SLURM is that SLURM specifies X11 support, while SRun won't have X11 support. And then you can obviously submit like a non-interactive job to the head node using SRun. For example, you use SRun and then you specify a container and you specify the script, and you execute your script through the container. So that will not require any interactivity, but the output of that job will be viewed in the terminal, as opposed to running in the background, which is what SBatch does.
Yeah. So, sorry, can I just extend and then we'll come back to your question? Thanks. So if you've got this prompt here in your terminal, that means you're on the head node, the login node. And so you'll see, as we demonstrated before, when you run SLURM, that actually changes the prompt to be the SLURM worker. So if you see this kind of syntax, this is a worker node. So this is where you can run processes, and it's using the worker node rather than the head node.
Yeah, perhaps my structure of my sentence, like don't run jobs in the SLURM node. No, it's not correct. Like you want to submit from the head node, but don't run software and don't run processes on the head node. Yeah. So the head node itself has only got 16 CPUs and a limited amount of memory. So, and that's purely for managing the jobs. So submitting jobs and viewing information about your jobs. If users are running software on the head node, it reduces the performance for other users. So just to clarify, you can submit jobs from the head node, but don't run software on the head node.
Right, and then if I SCP from my laptop to the SLURM cluster, I have to use the app transfer, otherwise it's going to be
Exactly, yeah. So Jacinta's second question was about transferring from her laptop to the SLURM cluster or the directory. If you're using SCP from your personal computer, you must use the transfer@ilifu.ac.za machine or service that's available, and not use slurm.ilifu, because otherwise you'll be SCPing onto the head node. That's correct.
Yeah. So, for instance, so we have this SBatch script, and that's what we would run. Oh, yeah, sorry, I'm not sharing the screen. Thank you. So this is what would run in the background that I demonstrated before. And so this, if you remember when we ran it, we didn't get any of the output in the terminal, but it wrote to this, I actually forget what it's called, demo job. So it actually wrote to this log file. Whereas if I so you see there's no SRun here, and that's because SBatch is explicitly putting you on a worker node. But if I then SRun this, then it would use the worker node, but it would interactively give me the output in my session on the login node, but the resources it's using is on a worker node. So I could do that. Or if I want to just have a completely interactive session where I don't need to SRun for every command that I do, that's when I would do this salloc. And you can see when I did this salloc, it then changed the prompt to be SLURM worker 101. So this is showing me I'm now on a worker node, and I can, for instance, so for instance, I could take that SLURM job script, and now without needing SRun, I could just do this kind of thing.
The singularity is available on all the worker nodes for the compute nodes.
Yeah, so
it's just sleeping for 30
yeah,
seconds.
It's sleeping for 30 seconds and then it outputs. So it's essentially, if you want fully interactive without needing to SRun every time, then do salloc. If you want, just to run one little thing with the output to terminal, do SRun. If you want to write a whole job that runs in the background and capture the output in log files, then use sbatch. I think generally sbatch is the best, and salloc is the best for interactive, but there is a place for srun as well. So you may, so it's now just output 9.
I feel like the difference is use case. So if you have a pipeline and it's going to be a 9-hour data process and data reduction, then submit using sbatch because you don't require to sit there watching your terminal. If you're doing some development, or if you're just checking the list obs for data that you perceive, then use srun and salloc to just quickly open a container, run some software, check that something's working, to debug something. So those are the two different use cases for that. Yes.
Yeah, sorry, thank you. Okay.
Do you want to just reiterate the transfers in the documents, just so that
what do you mean?
the user documentation about the transfers,
like show it
for SCP? Yeah,
sure. So Jeremy would just like me to reiterate. So if you scroll down on the ilifu docs to data transfer, it's got this section on transfer using SCP and rsync,
and there's an example from your personal computer SCP, and then the file that you want to transfer, and then it's your username at transfers.ilifu.ac.za. So that's how you would do it. So for an SCP, it depends on, yes, so you put your source first and then your destination. So you would just reverse that. You would obviously have to specify which file that's on the cluster. Like, so you would do /users/ your username and then the file name. And then your destination, if you can either specify the path, or if you've just docked, it'll place it, like a period, it'll place it in the current directory. But if you, for any of these tools, if you check the manual pages in the terminal, you can do man SCP and it'll give you information. You can go from there outside of the test. It'll give you information on how to do your copy.
And then there's also rsync, which uses SCP, but it's a little more advanced for regularly synchronizing directory structures and only putting, for instance, you can configure it to only put new files or files that have changed. You can exclude certain directories. There's all sorts of things you can do like that. It's quite useful, but again, it's slow because it uses SCP, not grid FTP. Are there, okay, yeah.
So Shilpa's asking if we can access the fact nodes through the Jupyter interface. So The Jupyter spawner that's available, that we've advertised, is specifically uses the SLURM cluster, whereas the fat nodes are separate virtual machines that are not associated with the cluster, so they don't exist in the cluster. However, each of those fat nodes does host a Jupyter session. So if you went to, for example, the VLPI Whiplash, if you went Jupyter .whiplash.ac.za, is it? Sorry, I'm getting confused.
No, yeah, it's just
Whiplash. Yeah,
IDIA.
Whiplash.idea.ac.za. That Jupyter session is sitting on the Whiplash fat node.
That would be in the browser.
Yeah.
Right.
HTTPS : and then whiplash.idea.ac.za. So it's the same URL or IP as you would SSH. Yeah.
Maybe I'll just speak loudly here. We do plan to phase out those fat nodes. We're still sorting out the problem on the current Jupyter spawner, which is preventing us from doing the complete migration, but the plan is to phase them out quite soon and then just use the Jupyter spawner approach.
Yeah.
Maybe you can repeat that if you could.
Yeah, if you couldn't hear that, just say in the chat and we can repeat. I also want to mention that you shouldn't use Whiplash unless you're in the VLBI group, because that has been set up for them, Roger Dean's IDIA VLBI project. So that's why we have the spawner, and it can give you sole access to the resources you request through the spawner anyway, rather than having to share resources on a fat node. Hence why we're phasing them out anyway. There's one question here, and then we'll take Jacinta's question. So question here was about whether you can monitor the usage of a job on the system, for example, a long process you've launched with SBatch, or some interactive session, or what you're using on Jupyter. There are ways to do this. So for instance, I showed you one way, for instance, using saccount. So if you remember, I had this summary alias. So this is basically this thing. So this, at a given point in time, shows me some statistics. For completed jobs, for instance, it shows me the max disk read and write. It also shows me the total CPU and the memory usage, the CPU time. There are other more advanced SLURM commands for basically sampling how you are using resources. And then maybe a little sneaky plug. Just let me find the slides here. Joe from IDIA has actually been developing some of his own kind of benchmarking and diagnostic software, which upon request you might be able to use. So this is basically a way to, over time, just map the resource. Yeah, and I'm trying to find it first. The resource usage. So just let me find the thing. Here we go. So for instance, this was something Joe did for a CASA task called tclean, which does the imaging. And so you can see as a function of time, it's showing the memory usage, which is the same statistic I was showing you is output from SLURM, although the way I was showing it's only the maximum at the end of a job. You can also see the read and write speeds on the two axes here in the two different colors, and then also the CPU usage. So this is something that you might be able to use upon request to Joe. You could just email our support at ilifu. We could make this available to you. We had another question here, Jacinta.
Yep. So two questions about Power. First is really looking to be able to plot positions. And the second question is where do you put the files?
Yeah, I'll take that. Okay. So the question was with Carter, are there plans to be able to overlay catalogue positions on an image, and where do we put the files that we want to view? The first, yes, there are plans to do that, all sorts of integration of VO tools and things like that. That's probably one of the later features that's planned, maybe for like late next year. You can talk to the developers, but they have a very detailed plan of feature releases coming up. And I think that's a much later one, although I think there might be some early support of just catalogs, maybe not so much VO services. And then, yeah, the on ilifu, that's in this Carter shared directories where you put your files. So for instance, we've got users, so we have all these users. We've added all the IDIA group users. So you should have one. Luckily, I can't view that. There's also Carter share groups, and upon request, we can make groups for you. This is the one I was looking at before. And then there's also Carter public, which is for basically sharing files. Generally, people won't use this, they'd use groups instead, because that way it will. So for instance, I shouldn't be able to view this one because it's got the permissions for this particular group on it. So that's the best way to do that. This is in the docs with basically writing to that directory. There's a strong one. Yeah, so for instance, this SLURM to write to, yeah, so Carter share users, username, image. So this is the way we suggest you do it, rather than copy like a FITS or CASA or myriad file to there. You would first, if necessary, convert that to FITS, for instance, if it's in CASA format, and then convert that to HDF5, writing directly to the Carter share directory, because that way we have to duplicate the data anyway. We may as well duplicate it to be in the format that it's efficient for Carter to read. Yep, so all IDIA group users we've now added, so you should be able to go to that URL, log in with your Jupyter credentials and move, yeah, write HDF5 files to that directory and view them in Carter. So if you want Carter, viz.github.io is where you go to read about Carter, how to use it and such. So it's got installation, but if you're using our server version, you don't need to worry about installation. You can just go straight to the docs, which is here. And you can read all about the different things you can do that I didn't really get time to demonstrate, but it's really quite a powerful visualization tool. Yeah, no API. This was, yeah, replaced by logging in with your credentials. So that way this manages what access to what data you should have. Yeah. Any other questions here or online? Yeah.
So the okay. Yeah, the question is using GPUs on ilifu and the best practices for that. So currently the GPUs are in a test state because we're testing the GPUs with CUDA libraries. So because we use containers or singularity containers, each container needs to have CUDA libraries that are specific to the TensorFlow version that is required. So at the moment, getting that working is in a test space. You might have seen on the SLURM cluster in the partition, there is actually a GPU partition which will be made available, and but we have not finished the testing phase, so we'll probably add that to documentation when available.
Just looking online here, I remember there was quite a use case at Oxford for using Carter. So David, I see you're there. If you don't mind passing on to your colleagues that they can all use their own login details to use Carter now and view their images without needing to copy the data to that Python machine you use and such.
Yeah, I can let them know. Yeah, it's very useful that, because previously what I was doing is, as you say, copying everything across, and I think it's be a bit easier now. So thank you.
Well, I think that's all the questions. Thanks everyone for joining us. Thanks for your questions, and yeah, you'll see these recordings and slides later, and hopefully you're able to make good use of ilifu from now on. Thank you.
Thanks, everyone.
Thank you.
Yes, thank you very much.
Thanks. Bye.